Black holes, where time and space converge under gravity's immutable power. These extremes of nature, once considered improbable, are now giving up their secrets. In fact, scientists have been able to imagine the impossible, the black hole at the center of our galaxy. We can now peer into the abyss. The concept of black holes was first proposed by the German astronomer and physicist Karl Schwarzschild, barely a year after Albert Einstein had published his works on the field equations of gravitation in 1915. Schwarzschild wrote to Einstein from the German trenches of the First World War, detailing his mathematical results of his gravitational equations. Sadly, the brilliant scientist later succumbed to a skin disease he contracted in the trenches at the age of 42. The existence of these so-called frozen stars was written about and debated for 50 years. In 1967, physicist John Wheeler coined the term black hole to describe these impossible objects and the conditions that would create them. New Zealander Roy Kerr advanced the concept by publishing a solution to the equations, which would require that black holes spin like all other astronomical bodies. Then Stephen Hawking and Roger Penrose theorized that black holes could emit radiation, now called Hawking radiation. The theory: if a black hole had no material to absorb and grow, then a black hole could evaporate, effectively shrink, and die. All scientists had to do was find one to study. Quasars, the tremendously bright, distant objects, were factored in as a strong case for black hole accretion, the only imaginable energy source capable of such incredible luminosity. In 1964, astronomers discovered one of the brightest X-ray sources in the sky in the constellation Cygnus, and labeled Cygnus X1. The powerful source didn't coincide with any bright optical or radio source, leaving it in the mystery basket of observations. Before long, with advancements in computers and space-based telescopes like Hubble, black holes were eventually detected, or their effect on their surrounds were detected, as black holes by their nature can't be seen.
Black holes are these incredibly fascinating but mysterious objects. We know they sit at the hearts of galaxies, and they drive how those galaxies grow and how those galaxies die. They swallow gas and stars up. They're also these incredibly enigmatic and mysterious objects that live at the boundary between our two great theories of physics: general relativity, which describes gravity, and quantum mechanics, which describes the smallest things in the world.
Black holes are literally gravity run amok. They are purely gravitational objects predicted by Einstein's theory of general relativity, and their most notable and terrifying feature is that things go in and they never come back out.
Wonder comes to my mind first. Such objects were never expected to exist in nature until very recently. As a matter of fact, I was a complete skeptic about black holes as recently as 20 years ago.
Black holes are places where Einstein's theory of general relativity is the whole story, not merely a perturbation on top of Newton's theory, which explains the dynamics of planets in our solar system. As a result, black holes provide a unique environment in which to probe general relativity specifically and strong gravity generally, and its implications across the cosmos.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen, all for free. No subscription required.
If you want to make a test of the fundamental theories of the universe, you want to go to the most extreme laboratories in the universe. And a black hole is that.
Seeing a black hole actually allows us to not only know they exist, and not only know an event horizon exists, it also allows us to test some of the very basic predictions of the theory of general relativity of Albert Einstein, which really describes space and time in its completeness. And that has never been tested before.
If you like Einstein's theory of gravity, then black holes are, one of the most interesting examples of this theory. And this is my role within this project. I am a theorist. I work with equations and simulations, and my role is that to try and understand whether the image that we produce corresponds to the predictions of Einstein's theory or maybe to something else.
From the physics side, I find that more an interesting question, that this is basically some kind of rent or tear maybe in space-time, and a place where we don't understand the physics and have a lot of serious questions about information theory.
I was very excited the first time I saw the first image. For a long time, this was purely theoretical. We were predicting that we would see certain features in the image, but we didn't really know, was it really there? And now we know, and it was exciting that all of that uncertainty collapsed in that moment.
So as the magnetized gas is falling onto the black hole, it heats up and therefore generates the light that we then see. Now, from our daily experience, we expect that light travels on straight paths and straight trajectories. We call them rays. Here, the situation is very different. We have a black hole sitting right there. So what the black hole is doing, it is deflecting and bending the light rays away from the straight paths that we understand in our daily life. And in fact, it can be so strong that we can see things that are behind the black hole that we thought are obstructed by it, just because the black hole is bending the light rays into our line of sight.
Scientists began running simulations on supercomputers. Multiple computational models were visualized to better understand what they might find in the data collected from their observations.
After we computed the radiative signature of our simulations, we have to compare them to the observations. And this can be imagined as you are in a stadium during a football match, and you have an image. And you want to figure out if this person or whatever is on this image is among the spectators in the stadium. So what you do is you take this image and try to match it with all the 60,000 spectators in the stadium. And you do this while you rotate it, you scale it, you increase the contrast, and you try to figure out first what is on your image. Is it a person, is it a cat or whatever? And try to match this to the spectators. And this seems trivial, but it's not. It's a highly computational, demanding process. So we need a supercomputer, which we have in Frankfurt. And we developed a so-called genetic algorithm, which is a very smart way running through these images and try to adjust them. And this takes roughly a month. And after this calculation time, we have maybe 10 of those spectators which match your image. And this is very similar to what we do in the EHT. So we try to compare and match our observations with the theoretical predictions.
So what is most surprising of this experience is that we managed to get a very good image the first time we tried to synchronize all of these telescopes at the same time. It is not so surprising that we obtained the image that we had predicted through simulations because, well, we believe our simulations are correct and because we believe that the theory of Einstein's general relativity is the correct one.
In 2019, they achieved their result, an image of the shadow of a massive black hole in the distant M87 galaxy. It was a world-first achievement celebrated around the globe.
I think we've been extremely lucky. I'd expected that we have to work for years and years, do many observations until we get a final image. And then we look at our first source and we see that ring. We see the event horizon and we see that shadow, that dark region, and you know immediately we're looking at an event horizon and a black hole from all sides at once in this thing. We see at a region where time stops. This is a very different part of the universe that we're seeing for the very first time.
We wanted to take an image of a black hole, and the problem with black holes is that they are very small. So you want to take a very big black hole, which unfortunately is very far away from us. And so you need a big telescope. This telescope is 100 meters in diameter, but it's not enough. You want a bigger telescope, and of course it's impossible to build, but you can create a virtual telescope by joining different telescopes in different locations, and so you can build a telescope which is as big as the Earth. And in fact, that's exactly what we've done. We joined telescope like this with telescope on the United States, and one even in the South Pole, to get a very sharp image, an image that is comparable to seeing an orange on the moon. Black holes tell you that there are regions inside them that cannot be explored. And for a physicist, this is very disturbing and attractive at the same time, because we don't like to have doors which we cannot cross. And in particular, inside black holes, physics is even expected to fail completely. And so this even adds fascination to these objects.
The future of the project will hopefully going towards a new understanding of more fundamental questions in physics. If this is true that black holes are the extreme objects where we can study gravity, and we know that general relativity, which describes black holes in the outer part up to the event horizon, breaks down at the event horizon. So the big hope is that with more data we might be able to study the physics beyond general relativity. So maybe there might be quantum physics ruling beyond the event horizon, or the combination of quantum physics and general relativity, which would be the theory of quantum gravity, which is non-existent at the moment, but we might learn more about this with the help of studying black holes.
Our experiments are like an Arctic expedition. We have to plan for months and months and months in advance, gather our equipment, and then we have this great migration of people to observatories all around the world. We stay up all night, we run our telescopes, and then we have this terrible period of waiting where we don't know if it's all worked. We send all of our data together, and only when it's truly combined do we know if it's worked. And then the even harder part begins of analyzing that data and being very, very careful, doing all the checks and balances to know that we got it right.
Data analysis, imaging black holes, and doing simulations is very exciting. It's also very difficult and requires a lot of patience. It's a very long process, but seeing the final product is very satisfying.
The Event Horizon Telescope collaboration is this amazing group of fantastic people from all around the world. Americans, Europeans, people from Asia, who've come together with all their technical expertise and scientific expertise to make this image of a ring around the black hole. The future of this project is amazing, because now that we've seen what we're after, we have so many more questions to ask about it, to push into the regime of, can we decide, is Einstein right? Can we study how gas really gets swallowed by the black hole? Can we see a giant eruption of radiation, of particles coming out of the system? So many things to do. We've really only just begun.
Now we want to make the first movie. Now we want to understand how space-time rotates around the black hole. We'll do that by putting more telescopes around the world to make our virtual lens even better.
It was a fantastic way of combining talents from different people in a way that otherwise would have not been possible. In order to take this picture, you need the cooperation, the simultaneous observations of many radio telescopes across the planet. You need to have the largest possible network of telescopes taking the same image at the same time.
New goals for the Event Horizon Telescope were quickly set. The M87 massive black hole is far away from Earth. Scientists wanted to get a closer look and decided to image another black hole at the center of a galaxy, one much closer but also much smaller and shrouded in gas and dust.
So if you try to look into the center of galaxies, it's usually blocked from view by dust and other stuff. In the radio, you can look through, like here today, we can look through rain, you can look through clouds, and so we can look through dust. And with combining radio telescope like this together with other telescopes in the world, you can peer right into the center of the galaxy and see this black hole.
The science result is it's just one point in time in the project, and we are always learning more about how the instrument works, how people work, how new theories come about, and so this is an evolution in my perspective. It's not just one point in time where you say, this is it, that's done. It always continues.
So we still have a lot of mysteries to be solved, problems to be tackled. There are still many questions about black holes, so I would like to study further the black holes.
The Event Horizon Telescope targeted the black hole in Sagittarius A, which is the location of the center of our very own Milky Way galaxy.
The long-term future of experiments like the Event Horizon Telescope is moving this kind of instrument into space and starting imaging black holes from space, which improves a lot this kind of observation because it allows us to have even higher angular resolution than what we have now. So we will be able maybe in 20 years, 30 years, make a very accurate images of the event horizon of a black hole.
Not only did scientists image the black hole, they sampled the radio emissions from the surrounding hot gases, giving us an audio impression, the sounds of a black hole.
So far, we've been looking at the closest massive black hole, but quasars, very distant from us, with gravity, we can see the motion of gas and resolve the sizes of these regions and thereby measure then the mass precisely. So if you can do this for many quasars, many distant objects, then you can solve perhaps the riddle how massive black holes played a role in the evolution of galaxies. We now know that basically every galaxy has at its center a massive black hole of different masses. We'd like to understand that in detail. There is, if you like, a symbiosis between these black holes and galaxies, and we need to understand that in order to understand the evolution of the universe.
Studying the data from the Event Horizon Telescope continues to reveal more detail. In this case, X-ray emissions reveal magnetic lines of force through the orbiting gas clouds. Further study of the X-ray emissions is currently underway with a new space-based X-ray observatory, the Imaging X-ray Polarimetry Explorer, or XP. Launched in 2021, XP is designed to observe extreme cosmic objects like pulsars, neutron stars, and black holes. This satellite is able to study X-ray radiation, which is polarized or oscillating in a particular direction. This reveals more detail of the physics of these high-temperature environments, particularly around black holes.
But there are two other parameters that we could look at if we only had the tools to do that, and those have to do with the polarization, the degree of polarization, and the position angle, the angle associated with the polarization. So by doing this mission, we're opening up 2 more degrees of freedom to be able to try to understand how are the X-rays produced, what are the models. We have to be able to predict the polarization that we will turn out to measure. So it's really exciting. Our science working group has studied we have 7 different teams of studying different classes. So for example, the radio pulsars, supernova remnants, etc. And so we're going to be looking at 7 different classes and several examples of those classes so that we get a good preliminary survey of what polarization is out there.
The extreme environments created by black holes are an opportunity to study many other phenomena. Neutrinos, the most abundant particles in the universe, have almost no mass and very rarely interact with matter. They seem to be generated in extreme objects like exploding stars and the fast particle jets ejected by supermassive black holes. Colliding black holes are another event closely watched, as they generate gravity waves that ripple through space-time and can be detected here on Earth. Another recent event detected was the flipping of the magnetic field surrounding a massive black hole. The reversing polarity caused the visual brightening of the material surrounding the black hole and the reduction of its X-ray emissions. During this time, the X-ray corona disappeared, and only when the flipped magnetic field gained strength did the X-rays emissions recover. Another black hole has been observed devouring a star that wandered too close. The ejected superfast jets of material interacting with nearby dust clouds and aiding to form planets within the material. These singularities appear to be an intrinsic part of both the destruction and creation of stars and planets. While we don't have all the answers, discoveries like this one set us on a path to understanding more about the universe. We have looked up to the stars and galaxies in awe and wonder for millennia, trying to understand our place in the universe. Current technology is enabling us to see further and farther back in time with much more detail than ever. The next generation of orbiting telescopes is soon to enter service. Who knows what giant leap they will make in our understanding of the universe. Since its launch in 2013, ESA's Gaia Observatory has been constantly mapping our galaxy, creating the most accurate and complete multi-dimensional map of the Milky Way. This latest observational dataset has been released and contains even more and improved information about almost 2 billion stars, solar system objects, and extragalactic sources. Our Sun travels at 240 kilometers per second around the galactic center and will take 220 million years to complete one orbit. The Gaia dataset includes stellar positions, stars' distances, and motions across the sky, plus color information, and most significantly, the radial velocities for 33 million stars within the Milky Way. This allows astronomers to create the most accurate and complete multi-dimensional map of our astronomical neighborhood. Another novelty in this dataset is the largest catalogue yet of binary stars in the Milky Way, which is crucial to understand stellar evolution. At the Observatoire de Paris in Meudon, Paris, France, scientists form part of the Data Processing and Analysis Consortium, some 400 scientists from 20 countries who are responsible for the processing of Gaia's data with the final objective of producing the Gaia catalogue.
So Gaia is extremely important for all fields of astronomy. The Gaia catalogs, that results contain a huge amount of information that will provide the material for the work of astronomers around the world and for many, many years.
With each new release, the observed stars, solar system objects, and extragalactic objects increase, and many more details are added to what is already the most detailed overview of our galaxy.
So Gaia is an incredible satellite which looks at the stars, which measure 1.8 billion stars, but obviously it goes from what is nearby, asteroids, up to very distant quasars. For these 1.8 billion stars, it's able to find their distance, their astrophysical parameters, their ID card in some sense. Up to now, Gaia had given already a lot of information about stars, but now it's going from astrometry, position, motion of the stars, up to astrophysics, knowing the characteristics, the astrophysical parameters for nearly 500 million stars. It is able also to find a lot of variable stars, to classify them. It's able, of course, also to see what is variable in terms of position, and so it helps to find binary stars which move on the sky or on the spectrograph.
And this time we provide new measurements such as star brightness in the RVS spectral range, rotational velocities, atmospheric parameters, chemical composition, and the RVS spectra also provide information on the abundance of the interstellar material that is present between stars.
So Gaia is observing with astrometric instrument which measure the position of the objects, and from this position it gets the motion of the object with time on the sky. That's astrometry. Then Gaia measure also the light of the object, measure spectrophotometry for the object, and from this it can infer the color of the object, but also you can derive from that all the astrophysical parameters that you can get, like temperature, effective temperature, gravity, and so on. You can also infer what is the extension of light in the distance where it comes from the star to us. So the third instrument now is a spectrograph, which is able to see the spectrum of the star. And so when you see the lines of the spectra, you see at which speed the object is going towards us or and the other way around. Or when it's moving periodically, then you can detect through the motion of this radial velocity. That's the three main instruments of Gaia.
Even older than Gaia is the venerable Hubble Space Telescope. It too continues to contribute to the science of cosmology.
To my mind, the most important discovery from Hubble is the discovery of dark energy. There have been a lot of interesting discoveries, certainly. Certainly the fact that there are billions and billions of galaxies that we had no idea there were that many. The work that we were doing on exoplanets with Hubble has been interesting. I mean, Hubble has carried such a wide variety of results that it's hard to pick a single one, but I do feel the dark energy is the outstanding discovery. And what that means is simply that space, we always thought that space would contract because gravity would pull it together. We knew it was expanding, but we thought the expansion would slow down. Well, instead, the expansion's speeding up. And that is a very exciting thing to me.
Because the Hubble Space Telescope is operating so well and is so scientifically effective right now, scientists are using Hubble to investigate some of the deepest mysteries of the universe. One mystery is dark energy. That's the name just kind of plastered on this phenomenon that Hubble and other telescopes together, we found that the universe expansion has been accelerating for the last few billion years. Well, what is causing that? We don't know. It's something about a repulsive force that we may not fully understand or new physics that we don't fully understand. But Hubble was used along in complement with some telescopes on the ground to determine that the expansion of the universe is in fact accelerating by something we're now calling dark energy. And without Hubble, we would have not been able to make this detection, which is now a Nobel Prize-winning discovery.
This explains why the universe appears to be accelerating now when it used to be slowing down because of gravity. So now the question is, well, is this a simple story or is it complicated? Is there more than one kind of dark energy? Has the dark energy itself changed over time?
So Hubble is now being used to refine even further that expansion rate of the universe in our current epoch, and trying to compare that to what might be predicted from looking at other measurements of the universe with other telescopes. Right now we're finding a discrepancy between what we might have expected and what we're actually measuring. So that's one realm where Hubble is really at the cutting edge of helping us understand, or at least open up, new mysteries of the universe.
Astronomers are still puzzling over dark matter and how it behaves. They have found small, dense concentrations of dark matter that bend and magnify light much more strongly than expected. Dark matter makes up the bulk of a galaxy. The gravitational influence of dark matter is thought to tie the galaxies together in massive clusters. There is so much regular matter and dark matter concentrated in these clusters that their gravity magnifies and warps light from distant background objects. By studying how the light distorts the background galaxies, though, this gravitational lensing can help map where the dark matter is in galaxy clusters. Images of lensing galaxy clusters are filled with the smeared images of remote background galaxies. The higher the concentration of dark matter, the more dramatic its light-bending power is. Smaller clumps of dark matter associated with individual galaxies in the galaxy cluster create more distortions. In some sense, the galaxy cluster acts as a large lens that has many smaller lenses embedded inside. But strangely, astronomers found that 3 galaxy clusters used in their study had concentrations of dark matter that are so massive that the lensing effects they produce are 10 times stronger than originally expected. Soon to be launched, ESA's Euclid mission aims to investigate this dark matter, dark energy, and the expanding universe in even greater detail. Euclid will image billions of galaxies with unprecedented accuracy out to a distance of 10 billion light-years. These measurements will enable astronomers to improve their understanding of the expansion of the universe and the growth rate of cosmic structures.
Euclid is a cosmology mission. It will study and try to better understand the geometry and the nature of the dark matter and dark energy, which is the peculiarity of Euclid. It's a telescope that will scan the sky with an accuracy that is unprecedented. So this is really something that no other spacecraft did before. This will allow to get additional information and to better understand the story and for the expansion of the universe and the growth on the cosmic structure.
Euclid carries a 3-mirror anastigmat design. The primary mirror is 1.2 meters in diameter. This type of design allows for a greater field of view, covering the visible wavelengths and simultaneously near-infrared spectroscopy and photometry.
It was a very important milestone because it's somehow the starting point of a new phase of the project, because so far the 2 parts that you can see, the upper part that is the payload module and the lower part that is the service module, have been developed and tested separately. So today with the mating we start a following phase, the next phase, with both the 2 main constituents of the Euclid spacecraft are together.
Indeed, this is a completely new design with a lot of challenges involved with this mission, and we have put together a team of about 120 companies in Europe, which are working together in good synergy for several years, and we are very proud of the results achieved today.
The mission is designed for a 6-year lifespan. However, an extension of a further 5 years is contemplated, dependent on the spacecraft's onboard resources.
With the mating today of the telescope with the service module, we achieve a major milestone in the integration of the flight satellite. It has been a long journey because the 2 elements have been developed independently for several years, and now for the first time they are mated together, and this makes us very proud of the achievement.
So the telescope was already delivered here in October last year and was put in the clean room on the fixture, ready to be mated. In the meantime, we finished the work to be done on the remaining part of the satellite, which is here. And today we released the telescope from that foundation and we move it to the SVM by crane. It is a very dedicated operation because the tolerances or the budget we have for the mechanical stresses is very small. So it's a very fragile telescope because it needs to be light. So it's quite fragile. So for this operation, there was a tight allocation for the stresses. And the stresses they measured at every step on the feet which support the satellite on 6 points.
Next step after this mating will be the integration of the solar array sun shield, which will happen around May this year. And at that point, the satellite will be in full flight configuration. And at that point, we will go to Cannes to conduct the environmental test campaign for about 6 months. The objective is to have the satellite completely integrated and validated at the beginning of next year.
After the mating, the next step will be the finalization of all the connection, electrical testing. Then in front of the telescope will be installed the sun shield and the solar array, and after that the eye gain antenna. Then the test campaign will start in Cannes. The full spacecraft will be tested in environmental condition, and at the end it will be ready to be shipped to Kourou for the launch campaign.
Launching around the same time as Euclid is NASA's Sphere-X mission. It will survey hundreds of millions of galaxies near and far, some so distant their light has taken 10 billion years to reach Earth. Also, it will search for water and organic molecules within the Milky Way.
Sphere-X is NASA's latest Explorer mission in astrophysics. It's a small telescope, but it has this unique and powerful capability of doing spectroscopy everywhere.
We are going to survey the entire celestial sphere and collect a data set that will help us answer 3 fundamental science questions.
It's going to tell us about the origin of the universe, the birth and formation history of galaxies, and the abundance of essential molecules such as water in the early stages of star and planet formation.
The great thing about Sphere-X is not only will we view the entire sky 4 times, but we will see it in nearly 100 near-infrared colors. And that's really never been done before.
According to our current understanding of the universe, we think that in the very earliest times, and I'm talking here a fraction of a second, much less than a nanosecond, the universe appeared to have gone through an accelerating expansion called inflation. And this is really a profound idea, and we're very interested to test it. And so one way to do this is to look at how matter is distributed over the universe. We want to map hundreds of millions of galaxies in 3 dimensions. What Sphere-X does, in addition to mapping out all these galaxies, is we cover the whole sky. So we can measure these galaxies over the largest part of the range we can see, which is the entire sky. And we want to cover the full range of distances from today to as far back as we can see.
We know there are about 100 billion galaxies in the universe, maybe more. But we still don't have a good understanding how these galaxies came to be. Did they all form at the same time? Did they change in size and luminosity or brightness over time? So the intent with Sphere-X is for us to figure out the formation history of galaxies, where do they exactly form, and how do they grow over cosmic time. And that information is crucial for us because that'll allow us to separate various theories we have right now on the formation and growth of galaxies.
Sphere-X will also identify targets for more detailed study by NASA's James Webb Space Telescope and the future Nancy Grace Roman Space Telescope. The Nancy Grace Roman Space Telescope is set to launch atop a SpaceX Falcon Heavy within the next few years. It will capture images unlike any satellite before it. The Roman Space Telescope will have the same image resolution as Hubble, but with 30 years of technological advancement, will cover an area 100 times larger. Roman will also view the sky in carefully selected wavelengths of infrared light. This will allow scientists to see through the obscuring dust to reveal hidden stars and watch the growth of galaxies over the last 10 billion years. Because Roman will be seeing further back in time, accurate measurement of distant stars is critical. A small galaxy close in looks similar to a large galaxy farther out. One method used by astronomers to gauge distances is something called a standard candle. A standard candle is a type of stellar object or event that emits a specific known amount of light. This works because light sources appeared predictably dimmer the farther away they are. So, for further distances, astronomers have to rely on the brightest of stars or events, in particular exploding stars called supernovae. There are a few different kinds of supernovae, but the best for standard candles are type 1a. These supernovae involve a white dwarf, the leftover core of a dead star, and one other star in a binary system. The white dwarf accumulates mass from its partner and eventually explodes, giving off a set amount of light. These beacons then allow scientists to accurately predict their distances. Roman will also use its broad view to search for planets around other stars in our galaxy. It will be fitted with a coronagraph which reduces the light coming directly from the star to separate it from the light reflected by the planet. The Roman Space Telescope's coronagraph doesn't block the star's light. It uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects distortions in the light beam. As the mirrors deform, the blobs of light slowly disappear, revealing brighter planets. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, the Roman Space Telescope will provide the first look at individual planets in star systems that might be similar to our own. The Nancy Grace Roman Space Telescope will also look for the fingerprint of dark matter and dark energy in the distant reaches of the universe. With an unprecedented combination of breadth and depth, it will open a new era in observing and understanding our universe.